Right, we're gonna start now. So we look back at the last class, just a quick preview. We actually derived the direction cosine for space truss, and we were developing the direction cosine for space frame. So we look into the space frame, the 3D frame member. We have three local coordinates, C, eta, and the monster. You have the starting node there on the left, ending node on the right. So the first 3 degrees of freedom, I set them up as the translation kind degree of freedom, and also that corresponds to the forces term. Whereas the latter 3 degrees of freedom are the rotational kind of degree of freedom, and that corresponds to the torsion and moments. Alright, so we set up the system just like so. We had quite a bunch of properties for your members. So you have the length, you have the E, you have the area, you have the torsional stiffness, torsional constant, you have the second area moment of inertia about the major and minor axis if you think about the steel design, and you have the shear modulus, that is for determination of the torsional stiffness. So I showed you this picture. We have the global coordinates in green, x, y, and z. So the local coordinates in purple color. Right, so you can see all of them, and well, this is quite a messy system, but if you try to look at it and take it easy a little bit, we write down the coordinates, the unit vector for the local coordinates, C, eta, and the monster, okay, as follows. Right. So this is the information that you must have ahead of time. I mean before the analysis. When you set up your structural member, you better know how the member align, how which axis define your major axis, which axis define the minor axis. So all these are predetermined before the analysis. Okay, right, anyway, these are unit vector. So you have the A, B, C, D, E, F, P, Q, R, and then we transform forces in global coordinates into the local coordinates. So you take sorry. Let me reverse it now. Sorry. Over here, we transform forces in local coordinates into the global coordinates. So you write F in global in terms of combinations of all 3 forces from local coordinates, and then you take the components of the vector into the global coordinates. So over here, I just go through just quick, okay. We have the local force F1, we have the local force F12, F13. So you want to take the component along the X, so you dot with the I. Alright, you get the components in X. Likewise, now you have the components in Y, so you dot with J, and dot with J. That's it. And Z. Okay. So over here we wrote the relationship, the matrix relationship between the global force and local forces. And you have this omega matrix. But this omega matrix is just for the sets of forces, right? So you do the same thing with the moment. You take the components of moment along the x, along the y, along the z. You end up with the same omega matrix. Okay. So, and you do this with another node. Okay, the ending node, because we just work on the starting node previously. But the same thing, exactly the same thing applies for the ending node. So we end up with this huge matrix, which is 12 by 12. So this 12 by 12 matrix is a diagonal matrix of the sub-matrix 3 by 3. So you have 4 of these omega matrices stuffed inside this 12 by 12. Okay, and this is nothing more than just the phi transpose matrix. Alright, and then we were here at the last time. So we successfully produced the relationship between global force to local forces. You have something in front of the local force vector. Over here now, we are trying to look into the scenario where we apply the global coordinate displacement and rotation, and then you will see how much it affects the local coordinate displacement and rotation. Alright, so it works that way. So you can see from the relationship we see right now. So we are trying to write the lowercase u in terms of uppercase u's and also uppercase rotation. Right. So we were here last time, and let me copy this to the class note for today. Okay. Right. So we develop this, then I'll write down the relationship in the following form. So you have the A, B, C. Oh, sorry, we have not finished this yet, right? Okay, then, okay, good. Now, let's see. So what we have here, the goal is to write first line. The goal was to, the goal was to write U11 in terms of global coordinate displacements, and that's why we dot the global displacement with the C, because C denotes this subscript 1. Alright? Okay. So that's what we finished in the first line, first equation. So the second equation, of course, what we have to change is the C into d eta. And then what will you end up with when you have eta dot, when you have eta dot with I? Okay, let's look at the eta. because okay, so eta is DEF. So eta dot with I, you get the D. Eta dot with J, E and F, like so. Later on, we move to the U1 subscript 3, so you have the monster. U dot with monster. So this monster is PQR. So you have P, you have Q, and you have R. Alright, there you go. So you stuff everything into this matrix equations, you will have the D, E, F, P, Q, and R. Right? That is multiply with the U, uppercase U X, uppercase U Y, and uppercase U Z. Right. So here is your uppercase U, lowercase u vector, and what is this one? This one is your direction cosine. No, not yet, not direction cosine yet. This one is your omega. Well, previously we have the omega. Let me add something over here. It's supposed to be omega transpose, right? Well, okay. So my writing is not quite as straight as I want today. Something. Okay, yeah, there you go. Looks good. So look at the omega matrix a little bit. Previously it is ADP, BEQ, and CFR. So right now it is a transpose of the previous one, right? So this is just called omega. Then same thing applies for the rotation. All right. So for your rotation, you have the relationship between the U1 subscript 4, U1 subscript 5, and U1 subscript 6. And then what we used last time was just the notations. All right. Okay, we have not defined that rotations, right? Hey, did I? For the rotation, I think I put the theta somewhere. Just bear with me a little bit. Let me check it out. I think I remember that I have the theta somewhere. I try to be consistent. F, okay. 2D planar frame. Where is theta? UX UM. Okay, all right. I cannot find. Okay. So the rotation U1 and U1 MX, MY and MZ. Okay. So just understand that this is the rotation. Okay. And now, what is this? What is this? Why is this here? Okay. Copy. No, I should cut it. Okay. And paste it here. So, okay. We have this following relationship between the U and the uppercase U. So U11, U12, U13. So now we write the U lowercase in terms of uppercase U successfully. And that is given by the omega. Just the omega. Not the transpose one like before. All right. And now, global coordinates. U2X, U2Y, U2Z. Regarding the video recording of this class, I have all recorded. The point is that I don't have time to reduce the size. So if any of you can help do that, that would be great. So the size generally these days, it takes roughly about 35 gigabytes for 1 hour record. 35 gigabytes is like what? How many? Maybe like 6-7 Blu-ray DVD, right? Blu-ray DVD. One movie is about 5 gigabytes. So 1 hour recording takes me 35 gigabytes. I cannot upload it anywhere. So if any of you know how to reduce the size of the video, well, it is just easy. You just Google it up and get some software to do. But if any of you would volunteer and will help me reduce that size into the, well, still the HD, the high definition, but not to space-taking storage size like this, well, that will be great, and that will be feasible to upload on, well, YouTube or on the Google Drive. The module seems to be too good. The first one that I used on the first recording was another one. Okay, not this one. This one is, I purchased it later after that one, and well, it is very good, but that's the problem. The file size is too big. That one I used in just one class. It has like a buttons, physical buttons we press, and I don't know what's going on in the video, if it records or not, and I might end up with nothing on the recording because I cannot see anything on the monitor. So that's the concern, and then that's why I changed to this one. But the good thing about that one is that it just makes like 1 or 2 gigabytes of the video recording, which is quite reasonable for the storage point of view, but not this one. This one is huge. Right, 20 seconds. Okay, here we go. We have the transformation matrix. Okay, so now you can do that thing. So along with this transformation matrix, we have the force equals to the transformation matrix transpose K, and another, okay, direction cosine global coordinates. Sorry, which one, sorry? Oh, sorry. It was supposed to be just P. Thank you. Sometimes single core CPU running too many things in the brain, and then okay, I accidentally put something there. Thank you. Yeah, so I love this. Okay, just let me know if I accidentally put something, and if my brain doesn't function that well, okay, something like that happens. Alright, now I think the problem is that this K, the stiffness matrix, because this is a stiffness matrix of the 3D frame, we need to develop it. You cannot, you don't have just that 12 EI, 6 EI, that 4 by 4. This one, the dimension is, 12 by 12, right? This guy here is what? 12 by 12 also, and 12 by 12, right? So this one, 12 by 12. How do we come up with this? So we need to go back and borrow this picture again from the previous lecture. So I borrow this, I copy, and I'll paste here. (2019) the 8th, 22nd, 2006. Element stiffness matrix for space frame members. Okay. Alright. So out of these 12 degree of freedom, we'll be working on it one at a time, one set at a time, right? So I will bring this page to here, edit. I just, no, okay, right. So first of all, the easiest thing we could come up with, we look at the degree of freedom with the subscript 1, which are the degree of freedom that are aligned with the axis. Talked about the axial deformation first, right? So over here I have this page. I will put this. So the first column associated with u, we are talking about the lowercase u because this is the element level, okay, local coordinate. So u11, u12, u13, u14, u15, u16, u21, u22, u23, okay. I'll move it here. And the other thing, these are associated with the local force, right? 1, 2. Maybe I can make it a little more roomier. 1, 2, F13, F14, F15. No, not enough space. Let me move it up. Oh, it's too big. Okay. Maybe you will expect the PDF of this one because this is going to be huge. Okay, so we will put our stiffness matrix of these local correspond to these local coordinates and forces, displacement and forces in the following. Okay. Start with F11, F21. Okay. So we have the axial deformation F11, F21. You are talking about this. That corresponds to the displacement U11 and U21. Alright? Okay. So your stiffness will be EA over L and minus EA over L, minus EA over L and EA over L. Right. I'll put it in blue. EA over L minus EA over L, and then minus EA over L and plus EA over L. That's it. Now, we are talking about axial force. Axial force will not be affected by the following. Axial force is not affected by the this one, nothing to do with axial force. Rotations, nothing to do. Transverse displacement, nothing to do, and rotations has nothing to do. I put the U up there means they are corresponding to these columns. The U vector will be actually on the right hand side, but putting it up this way, that makes it easy for you to see that when you perform the multiplications of the matrix and the vector, that matrix will correspond to which, that vector will correspond to which column in the matrix. And moreover, the U11 and U21 will not affect transverse force, moments, torsion. It will not. So we have zero influence of this thing over the following entries. And come back to force at the ending node along the direction C. Same story applies. Alright? So, this is beautiful. We partially get this matrix filled up. So now, we finish the force along the axis of the member. We can move next to the moment along the axis of the member. And what is that moment along the axis? It is torsion. Right, so we come back and revisit torsion a little bit. For a torsion, you still remember theta equals to ML or TL over JG, right? Well, you can go back and look at the derivation. So the moment is actually just the JG over L multiplied by theta, which is the twisting angle. Okay. So the torsional stiffness is this part here, JG over L. So for the moment we talk, or the torque we talk about here, we have the M equals to F1 subscript 4. Subscript 4 is the torsional or moment, alright. Also the F2 subscript 6. F2 subscript 4, sorry. Subscript 4, not 6. For the theta is a U1 subscript 4 and also U2 subscript 4. So these are the people who get involved with the torsion. So come back to here. Now we need torsion. So for a torsion, I use this color. I clean this. We are now looking at 1,4 and 2,4. 1,4 and 2,4. Okay. So JG over L. This one minus JG over L. Well, minus JG over L and JG over L. Okay. And again, we will just try to fill out the unused, the zero entries. So you know that the twisting angle in the member will not affect any other kind of forces, right? Transverse force or the bending moment. This is just a torsion. So you fill in 0. So this degree of freedom does not affect any other things, other kind of. And this column. There you go. Okay. So right now we have two things left. We have the flexures in about the major and minor axis. That's it. Okay. So look at this. I will break the pictures above into two. So the first one between the eta and C, and the second one will be the monster and C. Okay. So let me draw the member. Oh. Member is here. I copy this member. Paste there. Okay. You have this. We have this. The other thing is this and this. So let us look at these axis orientations. First of all, the easy view. If you look at this picture and we take just the plane of eta and C, you see this picture. If you look from the top, so this is your eyes, looking it from the top, you'll be seeing the monster and the C like this. I'll make this one, move it up. So let me erase this ugly eye off here. And since the orientation of the first one, the easy one, eta and C, is quite easy, we can fill in that 12EI, 6EI, and so on and so forth just right away. But just now we figure out what over here So this is U12, F12. This rotation is counterclockwise, U16 and F16. So likewise, U22, F22, U26, F26. So we will put the relationships between these four displacement and forces moments. Now, 1, 2, 1, 6, 2, 2, 2, 6. All right. Then we go to the next page. 1, 2, 1, 6, 2, 2, 2, 6. 1, 2, 1, 6, 2, 2, 2, 6. 1, 2, 1, 6, 2, 2, 2, 6. So we start from here. It will be 12 EI LQ. Here 6 EI over L square minus 12 EI over LQ and 6 EI over L square. Right, next is 6 EI over L square, 4 EI over L minus 6 EI over L square and the 2 EI over L. Next one, minus 12 EI over LQ minus 6 EI over L square, 12 EI over LQ and minus 6 EI over L square. Last one, 6 EI over L square, 2 EI over L minus 6 EI over L square and the last one 4 EI over L. And then we fill out the 0, 0, 0, 0, 0, 0, 0. Okay. All right. Now we have just 4 remaining degree of freedom. So we need to come back to the previous page again. We look at this. Now, your positive sign convention is going like this. Alright, you need to be consistent with the way you set up the axis, and it is unavoidable that you're gonna have this one that is pointing downward, because another set of axis has made some well, you following the C, eta and the monster, so this is how it works. These are, let me see, U1 3, U1 3, F1 3, that is U2 3, F2 3. Right, how about the rotation? Look at the rotation. The rotation is 1 5 and F5. Okay, F, and also again produce the counterclockwise. So U15, F15, U25, F25. The point is that your stiffness matrix will not be 12 EI plus 12 EI plus 6 EI minus 12 EI plus 6 EI, and the second line 6 EI, 4 EI. It will be different due to the setup of this orientation. Alright, so let us look at this matter a little bit. So it's like when you develop the stiffness matrix, you first look at this. I think we need to redetermine the sign convention. So originally you have this. Okay, and then the 1 unit displacement is produced over there. This is positive, right? So you have the 12 EI over LQ U1, not U1, U1 subscript 3. Okay, this is positive. With this positive U13 displacement coming downward like this, what do you expect for the moment? Moment will go this way, right? I think you can see how the curvature looks like, and if you see the curvature, you know that how the moment is acting on the beam to produce that curvature. So the beam is like smiling like that, and then you need the moment that produce that smile. Okay, all right. Now your F15 is what? It is negative value, because the positive sign convention of F15 is counterclockwise. Okay, in the axis, in the setup we see, but the moment which is the byproduct of U13 turns out to be on the clockwise direction. So F15, let me put it like this. 12 EI over LQ. The next one is minus 6 EI over L square. Okay, this moment is a negative. This one, of course, pointing upward for the force F23. Pointing upward means negative because the positive sign convention is going downward, right? So this is minus 12 EI over LQ, and last it is going like this, right? To produce the moment that makes the beam goes like this, you need this moment. So it is clockwise moment, which is negative, minus 6 EI over L square. Alright, I'll just draw the direction of the force and moment then. So move to the second case. The second case, you apply the rotation. Rotation was supposed to be the you have the sorry. Rotation was supposed to be Okay, alright. Alright, this one. Because your positive sense of rotation is counterclockwise. Now, rotation go like this, you need force to counterbalance and then maintain the beam at that point against the vertical displacement. You have force going upward on the left, on the right you have downward, and there you go, you will have this counterclockwise. So look at the force first. This force going how? Going upward. Upward is negative, right? So this is minus 6 EI over L square. Moment, yes, 4 EI over L. It is going in the counterclockwise direction. How about another force? Another force on the right hand side is pointing downward, which is positive. 12 EI over L cubed. And lastly, 2 EI over L. Now, we continue with sorry, 6 EI. 6 EI over L square, not L cube. Okay. Okay, thank you. We'll come back to this one here. So this point is secure, and then you apply the displacement downward. From here, your moment is going to look like this and like this, and force goes like that. Alright, start with force. This one going upward, negative sign, right? Minus 12 EI over L cubed. The next moment is going in the positive direction, which is counterclockwise. 6 EI over L square. And then the force 12 EI over L cubed. And last one, the last moment is positive, right? 6 EI over L square. 3 cases. Now the last case. So we have the apply rotation. So we have 0 rotation there, and like that. To do this, of course, the moment goes like this. But if the moment goes like this, you need the force to pull it down. Alright? If you have pulling down force, this one is pushing up, and the moment is going this direction. So let's start with the first degree of freedom. Force is pointing upward. That is the negative direction. Minus 6 EI over L square. How about the moment? The moment on the left is counterclockwise. It is positive, so it is 2 EI over L. Next, this force is going downward. That makes the class 6EI over L square, and the last one 4EI over L. Now your stiffness matrix is developed. Which is exclusively for this setup of the local coordinates. So let me put something down in the vectors. One three one five 2 3 2 5. Okay. 1 3 1 5 2 3 and 2 5. Right. And then we can fill the things into here. So 1 3 1 5 2 3 2 5. So start with the first line. 12 minus 6 minus 12 minus 6. 12, and then we will need to come back and look at the EI very closely. 12 EI over L cube, and then the remaining are minus, so minus 6 EI over L square minus 6 EI over minus 12 minus 12 EI over L cube and minus 6 EI over L square. Okay, then look at the second line. Minus 6 and the remaining are positive. Minus 6 2 EI over L. All positive, right? So 4 EI over L, and then 6 EI over L square and 2 EI over L. Go back and check the next line. Minus 12 and all plus. Okay. So minus 12 EI over L cube 6 EI L square 12 EI over L cube and plus 6 EI over L square. Last one, last line, minus 6 and then all plus. Minus 6 EI over L square 2 EI over L, and then 6 EI over L square and 4 EI over L. Okay, congratulations. We fill in the 12 by 12 local stiffness matrix. We need to do something with this a little bit. We need to put the subscript for I, because right now we just put the I, just the plain I. So let's see. For this one, the latter one, we are talking about the rotation about the fifth axis, the subscript 5, subscript 5, not the fifth axis, the second axis, the eta. Okay, you can see here. So the I will be the I about the eta. Okay. And the next one, this one, the bending in this frame F subscript 6 is about the monster axis, right? So let me put it down. Yeah, okay. Now, that's it. So we're going to take this 12 by 12 multiplied by the transformation matrix. The direction cosine is just 12 by 12 twice. Okay. So you can dream of the number of operations, which is quite huge to do all of these things. Okay. So here comes the time that we need to do something with the programming. I think we can start some lesson with Octave. Okay. So I think I will stop